Hi everyone, my name's Conor Svensson and I'm going to be here talking today about Web3j Java and the Ethereum blockchain. A little bit about myself first. I've been working within financial technology my entire career, most of that time on the JVM. I spent a number of years in corporate environments and then more recently moved into the startup space where I co-founded a couple of startups and then more recently created Block.io earlier on this year to focus on building enterprise blockchain technology to make it more straightforward for organizations to work with blockchain technology. I'm also very actively involved in the Enterprise Ethereum Alliance, which is a group of companies, both large and small. You've got the likes of Microsoft, Cisco, Accenture, Deloitte, UBS, Santander, JP Morgan, just to name a few, and then small startups like myself focused on Ethereum technology and its application within the enterprise space. I chair a couple of working groups there and also am the organizer of the Enterprise Ethereum Alliance London meetup. So if you're interested in this application of this technology in enterprises, it's a really great place to find out more about what people are doing in this space and so on. In terms of Block.io, at its heart, we're an open source technology company where we're very focused on building out tooling and libraries such as Web3j just to make it easier for individuals to work with right now Ethereum blockchain technology, but long term we hope to be blockchain agnostic. We provide a number of different, services to help support our business model. One of those is your classic consulting. We also build tools as well. We have a Blockchain Explorer, which is our first product that's available now for working with private blockchain deployments. We also provide support, and there's training courses too for working with Web3j focused on Java developers. There's a 2-day course, and that's due to be running hopefully in the new year here at Skills Matter, but the details are still being firmed up there. Okay, so enough about me, and let's talk about blockchain. So at its most simple level, what is a blockchain? It's a decentralized immutable data store. So it's decentralized in terms of the fact that it's running across a number of nodes in a potentially untrusted environment where these nodes can be any arbitrary machine, such as the case with the internet. In terms of the actual data structure, it's much like a linked list where you have blocks that point to what's called a parent block. And they continually back reference themselves and to traverse them. It's the same as a linked list where you follow these links and you can go all the way back to the beginning of the time. And within this blockchain data structure, you have a number of transactions, and that's what's represented here. So the key things to note are that we have block numbers, and these references are backwards because your latest block will always point back to the previous block on the blockchain. It doesn't know where the next block, what the next block looks like will be. And within those blocks are transactions, and there can be an arbitrary number of transactions. There can be 0 transactions, or there could be tens or potentially more. In terms of blockchain technologies themselves, they first emerged in 2008 with Bitcoin. Bitcoin, I'm sure everyone's aware that it's been in the news a lot because the price has absolutely skyrocketed recently. But Bitcoin solved the fundamental problem of how can you transact something with a monetary value without actually fully trusting the other party, without having to go via a trusted intermediary. And this was a challenge that no one had actually been able to solve until Bitcoin came along. And one of the key data structures that facilitated that was the Bitcoin blockchain. The Bitcoin blockchain held details of transactions that had taken place on the Bitcoin blockchain network. And that data structure was decentralized and distributed across nodes running on the public internet. Now, the thing with the Bitcoin blockchain was that it was really, and for really the main use case of Bitcoin is that it's focused on transacting a store of value with parties. And for this, it uses a primitive sort of scripting language which is focused on really, monetary transactions. There are some extensions that you can do to it, but fundamentally that's what it was designed for. Now, that was what's called blockchain 1.0. Blockchain 2.0, that emerged in 2013 when a Canadian Russian named Vitalik Buterin wrote a white paper for something he called Ethereum, which built on the Bitcoin blockchain technology, whereby what it did was it supported the transacting and so on, much like you had with Bitcoin, but it provided a Turing complete programming language for actually programming applications that could be deployed to that blockchain to run as self-executing code. And so this was like a significant step in the evolution of blockchain technology, whereby it suddenly opened up a whole new raft of applications there, and a load more companies jumped into this space as well, and they started creating their own blockchain 2.0 applications. So in 2014, the R3 consortium was launched. You also had Chain came along, the Hyperledger project, and a number of others. And then by 2015, the space had absolutely exploded. So this slide's 2 years old, but you can imagine in the 2 years that have elapsed since then, quite how much bigger it would be now to actually be a fair representation of blockchain, because it's just exploded the entire ecosystem. Okay, so I'm going to be talking about Ethereum because that's the technology that I guess is the original 2.0 blockchain technology, but I think also from the perspective of developers as well, it's the most interesting technology because of its inherent open nature. So Ethereum's known as the world computer. It's called the world computer because no one owns it as such. You can think of it as a very, very primitive computer that runs in a completely decentralized manner where people can run nodes that support the computer, but none of them actually, have ownership of it. Everything's done through consensus mechanisms, which require majority of the network to reach a consensus on decisions for a change to actually take place within it. It provides a Turing complete virtual machine, so you've got your while loops and these sorts of things which you didn't have with Bitcoin. So you you could potentially run arbitrary code, but there are limitations there which I'll come on to shortly. And it's a public blockchain technology whereby it runs on the internet in a very untrusted with potentially untrusted nodes talking to one another. But that being said, you can actually run it as a private blockchain as well, within between a number of institutions where they have their own private network or however they want to configure it. So with the public blockchain, there's what are called, there's the mainnet, which is like your production network, and then you've also got what are called test nets as well. So these are just your test environments. There's three main ones within Ethereum, and they all offer slightly different functionality depending on what you want to do with them. So within Ethereum, it's got its own cryptocurrency. In the same way that Bitcoin's got, the cryptocurrency is Bitcoin, in Ethereum, it's called Ether. So Ether is considered the fuel of the Ethereum blockchain. So if you want to run some code on the Ethereum blockchain, you need to pay for that. And the way in which you pay for that is using this cryptocurrency Ether, but it's also a standalone cryptocurrency in its own right. In terms of the market capitalization, it's constantly changing. When I first did this presentation a year ago, it was hovering around, I think, 1 billion USD. Now it's up to 39 billion USD. Whereas Bitcoin, well, I think a week or so ago, it was 150 billion, but since then it's going to have gone up probably by another 10 or 20 billion. The key thing is, though, that your holdings in this cryptocurrency Ether are associated with what's called a wallet. And that wallet is an address. And that address is derived from basically a public key. So in terms of your public key cryptography, you have your private key, you have your public key. Your private key can be used to decrypt messages that have been encrypted with the public key and vice versa. It's one of the classic properties of this public key cryptography. But your wallet within Ethereum is derived from your public key address, and it basically is a string of hexadecimal digits like that. There is some stuff happening within the Ethereum ecosystem to actually change this. The main initiative there is called the Ethereum name service, but I'm not going to be talking about that today. But if you Google Ethereum ENS, you can find out more about it. Okay, so in terms of the price of Ether and where it is now, it's hovering somewhere around 400 USD. It did hit 500 USD the other week, but these are incredibly volatile times with these cryptocurrencies, and they're kind of fun to speculate in, and this is why there's so much interest in the space. But it's not something that you want to be putting all of your money into. But nonetheless, to watch how the prices have moved and how this space has emerged as an asset class is fascinating, because it's nothing really has had this impact in recent times since the dot-com boom, but we all know what happened there. Okay, so if you want to obtain Ether, there's kind of two main methods. So within the production networks, you can go to one of these exchanges, such as Coinbase, and you can spend you can buy it just for you can pay in GBP or whatever else to actually buy some Ether, just as you do any other FX type transaction. Or you can actually mine it as well. The mining's a lot of fun, but it does use up a lot of power. So just to give you, a reference there, I built a mining rig. That was what got me first into this whole space. And you take a number of GPUs and you basically put as many GPUs as you can onto a single motherboard. I had 4 GPUs sucking up 1,000 watts of electricity constantly, and it adds a lot to your power bill, but it's a fun way to play with the technology. Fortunately, with the test networks, if you want to work with those, the constraints are nothing like as high in order to mine it, because they want to make it easy for you to obtain this, so you can just CPU mine these cryptocurrencies. Also with the testnet, because the communities recognize that having to mine crypto or go to exchanges and so on is another barrier to entry for working with this stuff. There's also what are called faucets too, where you can basically request some Ether as long as you attest using like a public account, such as your Twitter account or whatever else, and then you can be sent some to experiment with it. Okay, so I've mentioned Ether, the actual cryptocurrency associated with Ethereum, but that's basically what you had in Bitcoin. Smart contracts, they're kind of the key innovation that came along with Ethereum. And so these are computerized code that actually reside on the blockchain. So if you think about that conceptually, you've got this, this distributed network of nodes running, and you can actually write code that you push out to that network of nodes, and they'll execute that code. And in certain respects, it's not that different, say, from some of your big data applications where you can have your MapReduce, and it can, break down a task into a series of chunks, then, span it out among a number of, parallel processes, or it could be nodes depending on the implementation, then aggregate that stuff back together. But with Ethereum, what it is that, this is farmed out to the network. So these aren't nodes that people have sort of, set up specifically for you. You are pushing code out to that network. The network's executing that code. And if you build certain stops or don't build stops into that code, you can actually deploy code to the network that it's physically impossible for anyone to stop running on the network. And so it's quite a sort of game-changing technology in that respect, in that there isn't a plug that you can pull on it as such. And so hence within this space there's been some quite high-profile hacks as well, because people use these networks as a store of value, but then if they write sloppy code and push it out to the network, then they can actually lose cryptocurrency that's been stored in the network and was managed by a smart contract. And these losses have gone into the tens of millions. And so it's huge amounts, but it's very much so a new paradigm that people are having to get used to when they're working with this technology. So these smart contracts, though, they're basically pieces of code that live on the blockchain, and there's state associated with them, and then there's the actual code as well. When you can deploy one of these contracts, but then you can also transact with them, and when you transact with them, they update the state, and you just have a state transition that happens. If you think back to the earlier on slide where we were talking about the blockchain as a series of blocks which are append only, much like a database sort of transaction log, it's a similar thing with the state of smart contracts, whereby you have a series of events, and then the state of them is sort of aggregated, much like it is, say, with other paradigms such as eventual consistency, whereby you replay these events to get the current state at any point in time. So with the transactions that you have on Ethereum, there's a few different types. So as I mentioned earlier on, there's Ether. So you can send Ether from one party to another. That's one type of transaction. Another type of transaction is just pushing a new smart contract or deploying it to the Ethereum blockchain. And the other type of transaction is actually calling a method on one of these smart contracts that's been deployed to the Ethereum blockchain. So those are kind of your three transaction types. In terms of what that looks like from a more technical perspective, you have your transaction object here. So you've got an address of where on the blockchain you are transacting with. So if you're sending Ether from one party to another, you need to have a destination address. If you're calling a smart contract that resides on the Ethereum blockchain, you need to specify the address of where that contract resides. But then if you're deploying a new contract, you don't specify an address because you're creating something new and then an address gets generated in the process. You have some data. So this is basically your bytecode, much like within the JVM, you have bytecode that is interpreted by the Java virtual machine. You have bytecode which is interpreted by the Ethereum virtual machine. You have the value associated with the transaction. So if you're sending Ether to someone else, then there's an amount of Ether that you actually want to send there. You have the nonce, which is a unique identifier to uniquely identify the transaction and the person sending it, so you can't have double spending on the actual network. And then you have what's called the gas price and the gas limit. Now, gas is how you quantify how much you're willing to spend to make a transaction happen on Ethereum. So the gas price is how much you're prepared to pay per unit of computation on the Ethereum virtual machine. So every single operation has a cost in gas associated with it, in the same way that an assembly instruction has a cost in terms of CPU cycles, say, for how resource intensive it is. So it's a similar analogy with the Ethereum virtual machine and the gas. And then you have the gas price as well, and that's the amount you're prepared to pay per unit of computation. So those are kind of the two parameters there that affect how much your transaction costs. The gas limit is the upper amount that you're prepared to actually spend as well. So say if you had some codes that had a bug in it and for whatever reason, not that it would get stuck in an infinite loop in Ethereum's case, but say it could get stuck in an infinite loop, then the gas limit would say, what your upper threshold is that you're not prepared to go against. So once your code, the cost of executing hits that gas limit, then the actual execution of that code will be rolled back and it won't complete. So you have those parameters there to kind of control how much you can spend. So the amount of Ether on a transaction is never going to exceed the gas price times the gas limit. So you've got your transaction, and then the next thing is you need to sign it. So what this signing process is doing is it's signing a hash of your transaction with your private key, and then it's submitting that through to the Ethereum network via an Ethereum client. So the Ethereum client is just a node that's running on the network. That client will do some general validation to ensure that the transaction looks good. If it looks good, it will propagate it to the other nodes on the network. And then certain categories of nodes running on the network are what are called miners. And what those miners are doing is continually aggregating all the new transactions that haven't been processed on the blockchain and solving a computationally hard problem, which takes computing resource to solve. When they find a solution, they put their hand up, and then they create what's called a block. And that block is where the transaction lives, and then they get paid Ether for actually solving that. And that's how a new block gets created on the blockchain. So there are some challenges, though. So I've shown you in a simplistic level how you integrate, well, what you need to do in order to transact with Ethereum, and as per the last slide. But if you go back, you can see that for starters, you send this initial transaction, but you have no mechanism there of understanding when this transaction's been added to the blockchain. All you know is that it's floating somewhere around the nodes at this point in time. But when you want to have some sort of state, if you want to have state awareness in your application, you need to know when something's happened on the blockchain. By default, you're not going to be able to do that with this approach. You also have the fact that in Ethereum, its native native integer types are 256-bit integers. So if you think within within Java, where you've got your 32-bit integers, or you've got your 64-bit long integer values as your native types, in Ethereum the native types are 256-bit, and so there's in effect you've got to do everything in terms of big integers if you want to comply with how Ethereum does everything. And then it also has its own types as well. There's similarities with the native Java types, but they're not quite identical, so there's mapping that needs to happen there. There's different types of transactions. So as you saw before, a single type, there's one way of submitting a transaction, but that transaction could be sending Ether, it could be creating a new smart contract, it could be transacting with an existing smart contract. There's not really any mechanism there to differentiate between them. Then you've got the management of wallets as well, and so on and so forth. And really what it is that the more you dig down into how to integrate with it, the more you find yourself kind of going down a rabbit hole of having to overcome certain challenges, which no doubt lots of people will encounter again and again. So this is where Web3j comes in. So what Web3j gives you is that layer to simplify integration with Ethereum. So you have your Java or Android application, or any JVM app, being Clojure, Kotlin, or Scala, and you make use of Web3j to take care of this whole communication layer with Ethereum. The protocol used within Ethereum is called JSON RPC, which is a lightweight JSON-based request-response protocol, which is fairly straightforward to work with, but it's more these other specific points of integrating with Ethereum which add the challenges, rather than just the fundamental protocol layer of JSON RPC. So Web3j, it provides a complete implementation of JSON RPC for Ethereum. So if you go through the JSON RPC specification in Ethereum, you'll see there's 100-odd different methods. Web3j implements all of those. It provides abstractions for working with Ethereum wallet files as well. It also has Java smart contract wrappers too, so you can work with these Ethereum smart contracts from native Java code without having to understand what's encoding and decoding is happening behind the scenes. There's command line tools, and it's Android compatible too. More recently, the Web3j 3 release came along. So this was the biggest release in the history of the library, whereby the library is now modular. So before, it was not a specifically large jar, because I've always been very mindful of ensuring that the dependency set is minimal for working with it. But at the same time, if you wanted to use a very specific piece of functionality from Ethereum, you had to pull in the entire jar. So now that it's a modular library, with every release, new artifacts are published so that you can pull down just the components that you want, just to simplify that. You also have a consistent API between the JSON RPC calls and the smart contract calls. And so when you make calls, you can do them synchronously, asynchronously, or you can use the RxJava observables too. It supports the Ethereum name service that I mentioned earlier on, and supports a tool called Truffle, which I'll talk about very briefly later. I've always wanted to ensure that the library is really readily available to developers who want it. All too often when you're working with open source libraries, you run into problems where they've got like their own bin tray repository where it's only available from, and you might be working in an enterprise environment which is a bit more restrictive about what you can access. And so with Web3j, it's published to Maven Central, and it's also published to JFrog's bin tray. So these are the two main Java artifact repositories that are used. JFrog bin tray by Android developers, Maven Central, obviously by Maven by default, and Java devs. There's also downloads available for all of the artifacts, and there's command line tools as well that can be installed using Homebrew, which provides some additional functionality, which I'm going to talk about there. Unfortunately, there's no easy way to, with the command line tools, you've got to download the binaries if you're manually using Linux or Windows. Just I haven't had the time to actually package them up there, but if someone wants to do that, please feel free. So one of the things that has been an ongoing challenge with Ethereum and blockchain and everything else is how to make it as simple as possible for people to get started. So something else that I released a couple of weeks ago was a sample project. There's lots and lots of integration tests, unit tests, and so on within Web3j that enable you to understand how it all fits together. But that being said, that's good for understanding the individual components, but it can take time to understand which parts do what and everything else. So I've put together this sample project, the idea being that it demonstrates all of the very sort of core functionality of Ethereum, sending Ether from one person to another, deploying a smart contract, transacting with a smart contract, calling a smart contract to read a value out of it in a minimal amount of Java code too, just so that you can see how you can do these core pieces of functionality without having to get bogged down too heavily in the library. So that's a very good, useful resource, but it's referenced throughout the documentation as well and at the end of this. In terms of the modules for Web3j, there's a number of them. I'm not going to talk about what they all do because this is more relevant for people who are familiar with the different components of Ethereum. But the point is that these are all individual artifacts that are published with every release. Actually, one that I will draw your attention to is the tuples implementation there at the bottom. There is an Apache project which provides tuples in Java, but I've never had. I felt it was did more than what I needed to. So within Web3j, you've got a code generator. So if you want to generate your own, tuples library, that's kind of a minimal tuples implementation, take a look at that. Just because I feel that within the Java ecosystem, I've not seen something that's kind of as simple as the Scala implementation. So there's that's there as well, but it's used within Web3j for some functionality. Okay, so if we think about the transactions picture we saw earlier, when we're transacting using Web3j, you get all this extra stuff here. The main thing is that Web3j provides an abstraction layer. So if you want to transfer Ether, you have a transfer Ether call, and you specify the to address and the amount you want to transfer. You don't specify these other details. If you want to create a new smart contract, you call that contract in Java code and you tell it to deploy that contract. If you want to transact with a smart contract, you call a contract object and then specify the method on that actual contract that you want to call. And so it's all done using objects that specifically map to what the underlying intent is rather than having to think in terms of Ethereum transactions per se. And then behind the scenes, you get these remote call objects, which basically give you the flexibility to actually transact using a synchronous call, an asynchronous call, or an observable. So here's what we saw earlier in terms of the transactions. So Web3j then encodes this into this transaction object. It then signs it as well, and then it sends it through to the network, as we saw before. But the key addition here is this transaction manager. So whenever you submit a transaction, this transaction manager kicks into gear. And what that's doing is that that's continually polling the Ethereum client to get a status for the transaction. So then when the transaction gets mined and added to the blockchain, this transaction knows about it and then passes this back to the client. So you as a client get notified when the transaction has actually happened and has been appended to the Ethereum blockchain, rather than having to send it and not be sure whether or not it's actually been appended to the blockchain and therefore happened as far as the blockchain is concerned. All of this transaction manager, the components of it are very configurable as well. So there's different modes of operation that you can do, which is detailed in the documentation. If the default way of doing this doesn't match what you need. Okay, so say you want to actually get started with Ethereum and play around with some of this stuff. The first thing you need is an Ethereum client. There's a service called Infura, which provides Ethereum clients running on AWS. And you can sign up for free. It's currently a free service. They will at some point start charging for it, but at this point in time, they haven't said when that's going to happen, and it's been running now for a year or two, so it's definitely a useful resource to start with. Or you can actually run a node locally. So the two main Ethereum nodes are called Geth and Parity. Geth is written in Go, Parity is written in Rust. There is also a JavaScript client which you can use for testing purposes called Test RPC, but it's not connected to the real network itself. So my preference is that you work with Geth just so that then you actually understand what a real Ethereum node does. And these are just the command line parameters to do that. The other thing that you'll need is a wallet. So if you've installed the Web3j command line tools or downloaded the Web3j fat jar, you can run Web3j and you can say create a wallet. These wallet files, they need a password, and then you need to specify the location of where it's going to be stored. And it provides sensible defaults for this stuff, of course. And then this is what your wallet file looks like. So at the top of it, you've got your address, which is associated with the wallet file, which is derived from the public key. Then you've got the ciphertext, which is your encrypted private key. And then the actual type of public key cryptography here, they're using elliptic curve DSA curves for generating these. And then you have your various parameters that are used to actually encrypt this wallet file as well with the password. To see transactions on the Ethereum network, there's a service called Etherscan. And so Etherscan provides views on the public network and all the different test networks as well. And so this is what some transactions look like, where you associated with an address. So you have a wallet address here, you have a balance with it. This is a test network, not a real network. I've got nothing like that amount of Ether. And then there's details of transactions associated with this network. Okay, so that's the Ethereum sort of fundamental pieces. Now, if you want to work with Web3j, I've always focused on ensuring the library is kept as simple as possible from the perspective of users. And so this Web3j abstraction is kind of your key gateway for working with the library. So what you do is you start by building a new Web3j instance, and we've just got a factory method there, and then it takes, in this instance, we're using HTTP to connect to our Ethereum node, and that uses what is the default port that our node is running on. And then you call Web3j and specify a method name, any parameters if required, and then you've got the send async, or observable. And that's kind of the pattern that you use for calling these JSON RPC methods on Web3j. So to give you an idea of the sort of things that these JSON RPC methods provide, some of them are for sending transactions, but that's kind of hidden away behind the scenes within Web3j. But it could be, get me the latest block that's been added to the blockchain, and then you get a block object back, and then you can, view details of that. Or it could be get the balance of this account on the blockchain in terms of Ether. And so there's various different methods that you'll find yourself making use of if you're working with Ethereum blockchains. And so this is your gateway for doing all of that with Web3j. Okay, so super simple example here. What we're doing is displaying a client version. And so we're talking about our Ethereum clients here. So we build the Web3j instance. And I meant to say as well, so we're using the HTTP service here, but you can also connect using IPC. So if you're running on Linux or Unix, it's using a Unix socket file to actually connect to the process, or a named pipe on Windows. But if you want to do that, you specify a new IPC service and then the path to the socket file. And then here we're doing this call Web3 client version. So we're sending that. And then what this is doing is it's sending a request over HTTP to our Geth node that we're running and saying, please tell me what version you're running. And then this is it. It's saying we're running Geth 172, and that's the just basically your version stamp for the client there. So that's your really simple way of testing that everything's up and running. Okay, so if we want to send Ether from one account to another, again, we'll see this again. We'll always see this Web3j build at the start, just reminding you how to instantiate it. But then we have this credentials object. So this credentials object just stores our credentials associated with the Ethereum blockchain. So what we're doing here is we're saying, okay, let's load these credentials. This is the password, this is the wallet file, but these credential objects can be created from an ECDSA private key value in terms of as a big integer or hex encoded value or whatever else. But the point is you get this credentials object, and then what we do next is we call this transfer method, and we say we want to send funds. Here's our Web3j instance. Here are the credentials we're using. This is the address we want to send to. This is the amount we want to send, and this is the denomination that we want to use. So Ether is really, really granular. So the most granular unit on Ethereum is what's called a WE, which is, and there's 10 to the 18 of them in one Ether. And so if you think in terms of micropayments and all this sort of stuff, it's really, really granular what you can do here. And so there's all sorts of different denominations within Ethereum for Ether, and so they're all available too in Web3j. So we send that through, then we just print, when it's completed, Web3j will return, and then we get this transaction hash associated with it, and we get the block associated with it too. So that's what we're printing out there. So when these transactions happen, you can then go to Etherscan and you can see details of the actual transactions. And so here we can see that it was from this wallet address. We can see the block height, which is the block number, and then we've got the transaction hash. And these were the values that we got back here. And then you can look at the actual, sorry. You can look at the other transactions that were mined in the same block on the Ethereum blockchain. So these are all the transactions that were in this specific block. So the smart contracts in Ethereum, they're usually written in a language which is called Solidity. So Solidity is a statically typed language which is kind of C-like. Some people say it's JavaScript-like, but I think it's more akin to C. The idea is, though, is that much like any high-level language, you compile it to a lower-level language, which in this instance is Ethereum virtual machine bytecode, and there's a compiler for doing that. And so the point is that you write these smart contracts using Solidity, and then you compile them, and then you generate smart contract wrappers using Web3j, so you can then deploy and interact with those contracts on the blockchain from Java. So this is your hello world of Ethereum. So what we have here is we've got this Greeter contract, and so it's called the Greeter because you deploy this contract with a string value, which is its greeting, and then you can retrieve that value from it. It's got a parent contract, which is this mortal contract, and what this parent contract's doing is basically saying who created this contract in the first place when it gets deployed on the blockchain. And then you've got a kill function too, which enables the owner of the contract to basically disable being able to interact with that contract. And so here we have the actual Greeter contract. It's inheriting from its parent contract there, so it's saying Greeter is mortal. Then we've got this string value that's contained within it. We've got a constructor, which is public, and it's got a greeting that we pass in. And then we've just got a getter, which is this greet method, and this just returns the value that's stored within. So it's a straightforward contract, but again, Solidity is another programming language that you need to familiarize yourself with in order to work with blockchain technology. So we have our smart contract in Solidity, and so the next thing is we need to compile it. And so we use the Solidity compiler, which you install it, and then you just have sol.c specify your smart contract. At the end there, we provide these bin and ABI arguments, which basically tell us we need to produce a binary file, which is our bytecode, and then this ABI file, which is a way of, it's a JSON data structure that gives us details of the different functions, methods contained within the actual smart contract. And these are the two different files. So if we look at those, the ABI file, this is just a subset of it, but we have name, which is this greet method, and then this outputs a string value here, and it's a function type. Then we've got a constructor here, and we specify that the values that come in there as well. And we've got a binary file as well. I'm not going to explain any of the the bytecode there, but you get the idea. Okay, so in terms of that actual workflow, what that means is that you write the Solidity file, then you compile it, and then once you've got these binary and ABI files, what you do is you use the Web3j command line tools and say Web3j Solidity generate, and then specify where you've got these bin and ABI files, the Java package name for the generated code, and where your source root directory is as well for actually creating the class files. Within the JavaScript world, there's an application called Truffle, which is used very widely for people developing on Ethereum for developing their smart contracts. Within the Ethereum ecosystem, Truffle's the most mature tooling for working with it. But again, it's, if you're a JavaScript developer, that's great. But if you don't want to do JavaScript, then it's not so good. That being said, it does have some useful, functionality there. So, if you're working, say, with Truffle to do smart contract development, it provides a few additional bells and whistles. One of those is that it's got what are called smart contract migrations. So if you deploy a smart contract to a real Ethereum network, be it a production network or a test network, there's a metadata file behind the scenes that will get updated with details of that contract deployment. And so what you can do, though, in Web3j is you can take these metadata, contract metadata files that have been generated using Truffle and use them to generate your Java smart contract wrappers. So what that means is that your generated Java code will be aware of the previous deployments of those smart contracts too, so that you can actually, you can kind of switch between the two different environments for smart contract development if you want to. This is what our generated code looks like. So in terms of the naming conventions, it's all exactly the same as the smart contract. So we've got a greeter class, and this extends this contract class. Within that, you've got the binary data, and then you've got your methods that mirror the smart contract method names as well. Again, it's about trying to replicate exactly what's happening within the smart contract as closely as possible there, so that you're not sort of scratching your head thinking, hold on a sec, I had this method in the smart contract, what do I call it in my Java code? So it's consistent between the two to keep things as simple as possible. And then you've got these type references and everything else there. The reason that I'm showing you this is just to make you aware that what Web3j is doing behind the scenes is say, you have a string value that you want to send to a smart contract, such as in our greeter value. Now, a string has to be encoded in a certain way within Ethereum. So what Web3j will do behind the scenes, it'll take your Java string value, convert it to a string value that satisfies Ethereum's notion of a string, then it will encode it into the correct byte representation, then it will send it through behind the scenes to the Ethereum virtual machine and call the method for you, and then return the value back. And so this gives you type-safe encoding throughout the stack. So, I spoke earlier about the fact that within Ethereum it uses 256-bit integer types natively. So, rather than have to think in terms of those 256-bit types in Ethereum, when you're in Java, what you can do is you just specify, you can pass in like a big integer value, and then that will encode it and say it enforces it encodes it then behind the scenes into the relevant type. So, if you try and specify a value that's too large or invalid for Ethereum, the type nature of the library will prevent it from actually, being sent through. And so you'll never lose any precision with your numeric calculations in the library either. Okay, so this is your hello world on the blockchain. So again, we build a new Web3j instance, we load our credentials, and then what we do is we've got our greeter contract, so we're just saying greeter deploy, and then we pass in our credentials and the Web3 instance. We use a default gas price and gas limit. So remember, the gas price and the gas limit, they're the amounts you're prepared to pay per unit of computation, and they're the total amount of the total amount of computation you're prepared to pay for in the execution of this. This is our string that we want to pass to our greeter contract, and then we send that. That returns once this contract's been deployed to the blockchain. And then what we do is we just say, on our smart contract, we want to get the value of our greeting, we get that back, and then we print it out. So what that's done there is that's pushed this smart contract out to all these nodes running across the entire Ethereum blockchain network. Then it's actually made a call to that network to retrieve a value back as well. So it's a simple example, but behind the scenes, what's happening is this is working with that notion of the world computer, which is the Ethereum network. Okay, so building on this, one of the big areas with smart contracts has been around the tokenization of assets. So earlier on with Ethereum, there still very much there is a lot of focus on this. It's taking real-world assets and digitizing them and representing them in a smart contract on the Ethereum blockchain, and then being able to, people buy and sell units of those tokens as they see fit, and those track
that real-world asset. And so on our far right there, we've got an investor. They pay in Ether, which is, again, the currency associated with Ethereum, and they get back tokens. Smart contract manages those tokens, and then there's some underlying assets that's reflected there. There's what's called the ERC20 token standard within Ethereum, which is really a reference implementation for smart contracts that manage tokens. So when you hear about all these ICOs and everything else, they all use this ERC20 implementation. It's up here as EIP20 because these things will start off as Ethereum improvement proposals that get a lot of feedback from the community, and then they get formalized into specifications. There's lots of examples, though, of within the Web3j project, and you've got a specific ERC20 token implementation within Web3j and integration tests, so you can really see how that stuff fits together. But this has also been the driver for the mania of the initial coin offerings at the moment, whereby you have these organizations that are writing a white paper about an idea, or well, it can just be an idea. Some of the more mature ones in the space have actually got some sort of MVP out. And then what they do is they, in effect, have a funding round, which they call an initial coin offering or an initial token offering, or whereby people invest Ether and then they get tokens back that, in theory, will track the value of the company. And so if you look at the market capitalizations of these, because of how much cryptocurrency's gone up, it's ridiculous now. Like, you've got, based on the value that their tokens have exchanged hands at, you've got capitalizations of unicorns being created in this space. So it's ended up somewhat ironically being like the main, well, the main sort of use case of this technology of late, but it really is in bubble territory right now. One of the other things that Web3j makes a lot of use of is RxJava. So RxJava is the Java port of what are called the ReactiveX library. So this was something that was pioneered at Netflix, whereby they came up with a pattern where if you've got a series of events happening, what you do is you have what's called an observable, whereby this observable is something that emits sequences of events, and then you have what's called a subscriber that subscribes to these sequences of events and works with them. Because of the nature of a blockchain, whereby it's this append-only data store, blocks get created, transactions get created, there's stuff always happening there. It works really well with the whole observable way of doing things, because there's things happening on the blockchain, and it just provides a really nice abstraction for working with this. So you're not thinking in terms of polling to see if something's happened. Web3j can just emit events as you see fit. So I mentioned earlier on that all of these calls support observables. So in a really, really trivial example here, when we want to display our client version, so what we could do is we could create an observable and then subscribe to that. And so we put a callback in here that prints out our result. Not a great use of an observable, but at the same time, it just demonstrates how it's very much so ingrained into the fundamentals, the foundations of the library there. And there's the observables, they're really good for functional composability as well. So it makes it really straightforward to chain together lots of different things. And it's a very powerful abstraction for this stuff. So within Ethereum, with the smart contracts, you have what are called events. And so you can think of an event as a log statement. So say earlier on where we had the Greeter contract, where we pushed out a new version of, we deployed that contract. We could have what's called an event in there that says, I've just been initiated with this specific value. And so what you're doing is you log on the blockchain that this value has been set in that contract. You can use it as well, say, to track state mutation within a smart contract. So say, a value in a smart contract changes from A to B, you could log this event that says, this event's just happened, and this value's changed from value A to value B. And so these are events in Ethereum, and what Web3j gives you with the smart contract wrappers is you get you have basically these observables for all of the events. So if you want to monitor something specific taking place within a live smart contract that's deployed to the Ethereum blockchain, all you need to do is subscribe to that specific event. So you've deployed your smart contract, and then we want to know, say, when some sort of transfer has happened in that smart contract of, say, a token from one address to another. We can just call this transfer event observable, and then this will fire every time a token gets transferred from one address to another. So it's just one line of Java code to do that stuff, and so it's a really simple abstraction for something that's fairly complex happening beneath the surface. Say if we want to play around with what's going on within the blockchain, we provide abstractions again using observables within Web3j for that too. So what we have. We've got this block observable. So what this is doing, so we create our Web3j instance, and then we say, we want to create a block observable. We pass in false, and this is just saying that we don't want details of the transactions. We just want details of the blocks, because if you think the blocks have each got a number of transactions in them, and we won't necessarily want to get details of all transactions, we might just want to query the blocks. And so we call this block observable, we subscribe to it, and then it fires every time a new block gets added to the Ethereum blockchain. And in this instance, we're just saying what the block number is. But again, it's really, really simple ways of doing quite powerful operations, just being able to observe what's happening in real time to the Ethereum blockchain. You can also replay transactions as well. So say, if you want to replay the entire transaction history of the Ethereum blockchain, you can say, well, let me start at block number 0 and end at what is the current Ethereum block, hit subscribe, and then you can replay the entire blockchain in 2 lines of code. And then, of course, as well, we can replay all historical blocks plus all future as well, using the imaginatively titled catch up to latest and subscribe to new blocks observable. And I'm a believer in trying to be descriptive as I can with my code, but sometimes it does kind of stretch how long these method names are. But the point is, it's a single line there to be able to process the blockchain in its entirety and everything subsequently with it as well. And so that includes the transactions too. So again, it's about building on those, adding those increasing layers of simplicity so that it just makes this stuff more accessible for people to play around with and understand what's going on. And the performance isn't too bad either. So earlier on this year, when I first implemented this functionality, you're able to replay just shy of 1 million blocks in under 8 minutes. And all transactions, which would have, that would have numbered in the, it was definitely in the multiple tens, possibly hundreds of millions within 41 minutes. So again, sure, it's not super fast, but at the same time, from a practical standpoint, if you want to do an operation across the entire blockchain history, it's certainly not insurmountable there. So that's the core functionality of Web3j. In terms of the actual wider ecosystem of the library, I mentioned earlier on that you've got of course, there's the Java version of it, you've got the Android port. Now, the Android port's maintained on a separate branch, but it is completely up to date with the main Web3j Java. When I first started the library, one of the options there was to write the whole thing in Kotlin. Some people had suggested that, but my view was always about making this as accessible to as many developers as possible. And much as I do like Kotlin, I think it's important too that when people are trying to work out what's going wrong or debugging problems, the more accessible that is, the better, and the more it opens this up to a wider group of people. There's also a Spring Boot starter for it as well. So if you want to use your, you want to have your configuration in a YAML file or property file or whatever you're using with Spring Boot or XML, then you can do that so you don't have to instantiate the Web3j instances yourself. There's a Maven plugin. I'm hoping that someone will create a Gradle plugin as well. I've got instructions for what needs to be done to do that. It shouldn't be too much work, but again, it's just about trying to get members of the community involved with this, because really I've got it this far mainly on my own efforts, and so the more people that get involved with open source projects, the better. And then there's Quorum 2, which is JP Morgan's derivative of Ethereum, which is focused on sort of enterprise deployments. There's a specific wrapper there that caters for the Quorum-specific functionality that you don't have in wider Ethereum. So all of the projects are available on the Web3j GitHub piece, but those are the different names there. And finally, if you want further information, you can start off with the Web3j homepage. There's the sample project that I mentioned earlier on. I've spent a lot of time on the project documentation as well, which is available at docs.web3j.io. And when I say a lot, I mean that there's many, many pages of documentation that were all updated as well for the 3.1 release, so it should all be current. There's also good test coverage. It's around about 75%. It's slipped down from over 80% just with the 3.0 release, but it'll get back up there soon. And then there's a chat room in Gitter as well. So I think there's probably a few hundred people now in that chat room. So there's a fairly active community around it. And then, of course, if you want to talk to me directly, just please feel free to email me. And yeah, if you want to look at any of the products that my company's developed, you can see an overview of who we are at Block.io. That's yeah, all I have to say. Are there any questions? Yeah.
Hi. Great talk, by the way.
Thank you.
So I have a couple of questions.
Yeah.
One is, what are your thoughts on ERC20 versus ERC223? And the other one is, do you know of any way within Solidity or even with Web3JS or Web3j, whatever, that you can issue a token that you created without receiving Ether?
Okay, so the first question there was about the differences, well, my views on ERC20 versus ERC223. Now, which one was 223? Remind me.
There's a big issue with ERC20 in the sense that if you send any Ether to the token, it then gets locked into the contract. It then gets locked into the token and then can't be released. Some of the big ones like IOTA and EOS currently have about $250,000 sent to their contract address that now can't actually be sent back.
So it's more much like with the problems with parity around being able to get Ether that's got locked in the blockchain. Right. Yeah, so I'm not overly familiar with where it is at the moment anyway in terms of the improvement. So just for context, within the Ethereum community, there's lots and lots of improvement proposals that are actively being contributed to help increase the just increase the functionality around Ethereum. So one of the challenges there is that it's not a very forgiving environment whereby if you make a mistake, such as you accidentally, when you send Ether, you've put whatever you're using, you put a to address of 0, for instance, then it's unrecoverable because no one actually has that wallet address, but at the same time, it is a valid address that you can send funds to. And so what's the person here was talking about was that with certain smart contracts that companies have deployed, people have accidentally sent Ether to them and then they can't recover it. So this is about improvement proposals to work around those issues. And so that specific EIP, it's not one that I've spent time reading over, so I can't really say on that side of it. And your second question was just around being able to obtain tokens without actually having to spend Ether.
Yeah, so if I wanted to give tokens based on another criteria, so if you visit my website, for example, if you visit the website, then and you come in and you just put in if I wanted to give away free tokens, for example, you could come in and you could, in theory, put your wallet address in, and I could then send you free tokens from my contract.
Yeah, okay. So this was about other mechanisms whereby you could actually obtain tokens without sending Ether. And so this is where a technology called oracles is useful. The idea with an oracle is that it's an external service that a smart contract can integrate with in order to get an attestation that something has happened in the real world. And so by integrating with an oracle service that's met the needs of your specific use case, that would be the most logical way that comes to mind for achieving that. That being said, the main company right now is a company called Oracleize, who provide these trusted attestation services. But Microsoft have also got a technology called Cryptlets as well that is being released imminently, which provides a similar sort of service. But this is one of the challenges with blockchain technology and smart contracts at the moment. You've got this great sort of cryptographically secure environment for transacting, but then it's very, very slow. You can't process, say, I know, market data updates or tick something that's very high frequency, or there's a large number of within a smart contract, because it's like a really, really slow computer. It's more akin to like a 70s calculator almost in terms of performance. So yeah, there's definitely challenges there, but these oracles would be, in my view anyway, the way to go about that.
I'm already using oracles in order to verify the outcome of whether somebody's done that.
Yeah.
But I can't get the contract as yet to issue without receiving Ether. It seems to want to be paid for in order to issue my...
The oracle wants to be paid for?
No, the token.
Yeah.
Needs, so far, my experience, my exposure to Solidity has been, it receives, you send your Ether, and then as a byproduct of that, it then sends out your let's call it J-coin.
Yeah.
Sends out your J-coin because you purchased your J-coin with your Ether.
Yeah.
I've not yet done the one I'm trying to do right now, which is giving it away for free based on Oracleize conditions.
Yeah, yeah. So, I mean, with the standard sort of ERC20 contracts, you can, it's really down to the owner of the contract to decide what conditions they provide tokens to another individual. So you don't have to send Ether as such. It's more just if the implementation you're working with says that you have to send Ether to get a contract. But if you look at the standard. Consensus have the human standard token, which is their reference implementation, and then also Open Zeppelin, they've got their reference implementation too, and those don't require Ether in order to receive a token. You have to use Ether in order to pay for the transaction, but yeah, there's not really a way around that.
So it's essentially it's just a part of Solidity I haven't explored yet.
Yeah, okay. So, there's a question at the back there. Okay, so examples of actual smart contracts and what they do. It is an area that there's a lot of different people are experimenting with different things, and one of the real challenges is that people are saying, blockchain's this great transformative technology. Let's take this existing thing and put it on the blockchain, and because it's on the blockchain, it solves everyone's problems. But then they don't think about the fact that often the hardest problem is finding customers to actually pay for a service. And so there's a number of companies that are coming up with smart contracts that just replicate existing businesses, but it's decentralized and therefore no one owns it, so it's great. But the reality is that in terms of the killer applications, which I think is probably more pertinent to the question that you're asking there, I think they're still emerging. In the last week or so, there's been a big explosion. It's taking up over 10% of all transactions on the Ethereum blockchain is the CryptoKitties phenomenon. So what a company have done is that they've created a smart contract that enables you to create CryptoKitties, which are just cats that have a virtual identity, and that's exploded, and so 10% of transactions on the Ethereum blockchain are for these CryptoKitties. But the funny thing is that this is probably the first use case, the first game that's actually been very successful and had a significant following. The company that's providing the infrastructure gets a cut of every time a kitty is created, so they've got a business model there associated with it. So it's a useful case study to be aware of. In terms of actual, successful companies, profiting off this, I'd say the only people who are profiting heavily are, those doing the ICOs with those people who are, paying Ether to get some tokens, because we're not at that point where really any of this, well, CryptoKitties is genuinely probably the nearest thing that's had a critical mass type, usage on Ethereum. But that being said, there's some very interesting, companies doing other projects on Ethereum. So one example is EtherRisk, and so this is a company where they provide basically a flight delay insurance. And again, it's something that could be done using, without the blockchain, but the reason they use the blockchain is to make it a completely automated process. So what they have a smart contract. You specify when your flight is and your flight details, and you pay a certain amount of premium, and then they'll, using your traditional, some traditional insurance, I guess, calculations they do to figure out risk of a flight being delayed, they specify a payout associated with that. Now, what that contract does is it actually calls out to this Oracleized service that I mentioned earlier on, which tells them if a flight has been delayed or not. So as soon as a flight is specified as being delayed, then this contract pays out automatically. There's no intermediary or middleman or anything like that that actually is, in the middle saying, oh, well, actually it was only delayed by a minute, so, we're not going to pay out. It's a very black and white thing. And so, that's an example of a good use case. Some of the kind of more broader use cases that people talk about, one of them is around identity management and document verification, for instance. So, right now you have custodians of data in terms of, I know, at the academic institution that you studied at, they produce degree certificates. And so, someone asks you to see your degree certificate for a job, and you doctor it, and then you send it through, the person looks at it and says, yeah, it looks okay, but they don't have necessary proof without going to that institution to say, is this a genuine document that you issued? Now, with the blockchain, what you can do is that you could have a hash of that certificate, which is obviously, globally unique, that lives on the blockchain. So then, if I go to, I want to verify a specific document that was produced by this specific university, they could, you could specify the hash of the actual document, and they could attest that that hash matches the original document without having to dig it out. So, that's one of the use cases. Another is around identities. Right now, if you sign up to a service, typically, you're going to be maybe using your Google credentials, you might be using your Twitter credentials or GitHub, or, whatever else. But these organizations all end up being custodians of data about yourself as the individual. But you could have an identity that resides on the blockchain that is, pseudo-anonymous in terms of it's, an address on the blockchain that that you can make specific information available to other individuals, but they don't actually know who the identity of that person is. I mean, that's a more sort of conceptual idea of what's possible, but it's, it still is early days. So people are trying to, take all sorts of existing use cases and apply them to the blockchain, but it's not at that point where there's, lots of, examples you could say, yeah, that's definitely working. But, CryptoKitties has been an interesting one this last couple of weeks. Yeah, just here.
So basically, with the guest tool, you were able to spawn a client, a node, or effectively. So what would prevent me if I wrote a rogue client to spawn millions of them on the internet and to take over the network and steal things? Yeah. What's the security against that?
With the Ethereum network, and sorry, the question there was, what's to stop an individual creating lots and lots of geth nodes in order to actually, that are rogue in order to sort of take over the network. And so I suppose that there's two sides of it. One of them is, your attack vectors in terms of, DDoS attacks and just seeing who all the nodes are and just being able to, spam them constantly. And the challenge there is just having enough computation power to actually, hit all of those nodes that it actually brings down the network there, which no one's been able to do thus far successfully. What has been a problem before, though, in the test networks is around transactions. So the reason that the Ethereum network and these blockchain networks, they use these computationally hard problems that in order to decide, when transactions and, by extension, new blocks get created and added to the blockchain. Now, the reason it's computationally hard is that by being computationally hard, you need to be able to throw a lot of computing power and therefore electricity behind the problem in order to solve it. And so unless you have the computing power that is equal to over half of the actual network, you're not going to be able to get that majority there, which is going to cause the network to follow your malicious route there. So it's one of those things that just isn't attainable given the size of the actual networks there.
You mentioned basically the 51% attack.
Yeah.
I'm wondering, this is something that a lot of people I've spoken to have brought up the issue of, and it's something I personally am concerned about, both with Bitcoin and with Ethereum. Currently, obviously, with our current computing power, 51% attack is not really plausible. However, once we manage to get a SHA-256 hash running on a quantum computer, it's going to potentially become an issue now.
So the question there was just around what the previous point was, where you're talking about these majority attacks on the network. They're called 51% attacks. And the question here was about, how has quantum computing got implications for all of this? Because ultimately, these computationally hard problems are making use of cryptographic hashing functions. I'm not going to talk about how they make use of that, but that's kind of one of their underlying mechanisms. They're just doing these hashes again and again and again. And if you have a quantum computer, they could, in theory, reverse engineer these hashes, which right now is, computationally impossible. There's a lot of cryptographers who are, paying very close attention to the quantum computing space. I mean, the current sort of breed of quantum computers that are available, people aren't really concerned about their computational power because they're not true quantum computers. And I think really it more comes down to, cryptography as well, just cryptographers globally. They watch this space very closely, and because they're acutely aware that as soon as if someone is able to create a quantum computer that can break these current cryptographic standards, then it affects everyone. So the key thing's always about setting the parameters of the curves and everything else that are used, and specifically high, so that given what people know about what's going to be possible based on the current rate of improvements, much akin to Moore's law historically, how long it will take for those to catch up, and just ensuring that the complexity of the cryptographic operations stays sufficiently far ahead. So it's just that ongoing sort of cat and mouse game that's really always been something to manage with cryptography, because you've got to have the pragmatic side where crypto stuff can be done at a rate that's not so slow that it inhibits users, but at the same time you've got to have enough leeway there so that when the next big innovation happens, it doesn't actually slow things down. So I guess my own personal view is that that's what the cryptographers are they're very acutely aware that their whole industry would just fall apart if they didn't stay sufficiently ahead of all of this stuff. Yeah. The back there.
Can contracts call other contracts?
Yeah, so contracts can call other smart contracts. In the Solidity documentation, you can see details of that, but the key thing is you need to know the address of where that smart contract's deployed. So one of the a feature whereby you might want to do that, say, is if you've got smart contracts that are deployed that are have library functions on them, and then you can call out to those library contracts to actually do some computation for you. Okay. There any more questions? Yeah, one over here.
So I became aware of this 51% attack, and to me it looks like it's on the miner side.
Yeah.
Is there an example of attack on the other side of, let's say, the Bitcoin, of people that has lots of Bitcoins and is able to rule the network, not from the miner point of view, but from the one that has the currency?
I mean, it's certainly a valid risk in that if you have an individual who has, who owns a huge amount of Bitcoin or Ether or whatever the cryptocurrency is associated with the network, they could use that to malicious ends. But then you've got to think in terms of how much that's actually going to cost them in real terms. And so, it's certainly a real risk that someone who maybe got in really early, and bought loads of Ether could actually attack the network and do malicious things around it. But at the same time, really all they could do is just back up the number of transactions that are on the network. But then, are they actually going to want to use this cryptocurrency that's worth all this money to them just to wreak havoc with the network, because eventually it will run out, or they'll
Maybe temporarily ruling the network for a small amount of time.
Yeah.
And somehow take advantage of this.
Yeah. Well, with such an approach, I mean, if you think about who the different players are within within the blockchain, the public blockchains anyway, you have those individuals that actually own lots of the cryptocurrency, who you could think of passive actors on the network. Then you've got the miners as well. So if something's happening to the network that's affecting the network as a whole, apart from these small individuals, all you need to do is get a majority of the miners to agree to a change in the rules to say ban that individual or ban transactions that have originated from that address, and you've got a workaround. The person who is being malicious might not be happy, but they're one person, they're not the entire network. So it's this whole thing about through the majority of the network facing a very difficult situation, then they can come together to find ways to solve the problem, because that's in everyone's longer term interests. Yeah.
So in response to that, I think there's a couple of things people can look at for that scenario. One thing is recently it was suggested that Satoshi Nakamoto, the guy who invented Bitcoin, could potentially, if he wanted to, create that situation within Bitcoin, because he has somewhere in the region of like 1.5 million. So if he was to offload half of Bitcoin immediately, that could create a massive effect within probably the price of Bitcoin, not necessarily the network of Bitcoin, but certainly have a massive effect on the economic state of Bitcoin. One thing as well is what you would think from the client side of things as well, there's exchange attacks. Because a lot of people, you can either store your public keys in your personal wallet, or you can have an exchange store them for you. A couple of really big notable cases of the biggest one, of course, being Antigox. Antigox was the former largest holder of Bitcoin, and they got hacked, or there's loads of things that they claim they got hacked. Maybe they stole their own Bitcoin, who knows? But yeah, there's a number of even recently there was an exchange that got hacked. I think it was called Bit something or other. Yeah, so the biggest way to steal Bitcoin, if you were, would be to steal somebody's private keys.
Yeah, but that's outside the blockchain. Like, it's an issue with websites and stuff like that.
Oh yeah, for sure. Like
I
with
mean, it's not
websites.
blockchain itself that has some sort of fault.
No, but when you have access to an exchange, you have access to a large section of people's public keys.
Oh. Were there any other questions? Yeah.
So is there a size limit on the, because I have the feeling that you're saying that every time you want to do something, you add it to the blockchain. I mean, if we run this for 10 years, are we going to reach a point when it's so big that it becomes, the performance is so bad that it doesn't make sense to use it?
Yeah, at the moment, the blockchain, it's not trimmed or anything like that. It just keeps growing and growing and growing, which in the near term it isn't so much of a problem, but yeah, absolutely in the longer term it will be. Within Ethereum, the bigger problems right now are around just overall performance and just scalability to increase the transaction throughput. And so there's increase the actual throughput, but then also just the, how quickly they can actually happen individually too. And so the main thing that's happening there anyway is there's discussions of sharding and then also taking transactions off chain. So there's lots happening in that space. And Vitalik Buterin, he's recently done some talks at DevCon 3, the Ethereum Developers Conference, about where Ethereum's going in terms of its 2.0 vision. And it's like the plan right now is to kind of split the network into having a more experimental part and then a more core stable part. And what you're going to see anyway is that people will either be building new blockchain technologies on top of Ethereum, but also that they'll be coming up with new ways to transact, which take things off chain or take things off to private chain that then replicate certain information back onto the public chain. So it's very much an evolving space because the technology is still so new, and so there's lots of challenges still to be overcome. Okay. Oh, yeah. In terms of the execution of the smart contracts, what happens is that the actual the bytecode gets interpreted by the clients just to kind of validate it, but it pushes it out to the network, and what happens is that the miners see all of the transactions that are happening, and then they see the transactions that are pending and first try to put them together and to create a new block. Then when that block gets created, it then gets propagated to the other nodes on the network, and then they read the transaction in that block to update their own internal state database, and that has details of the state of the smart contract. So the miners just, they pull together. The client initially validates that some of the information on the transaction is valid in terms of that it's a valid transaction object, but then the miners pull together the transactions. Then when they've been put into a block, then everyone knows to update our state to reflect that, because then it's on the blockchain, whereas before that it's just kind of floating around. Okay.
So the contract cannot be executed before it gets added to the blockchain?
The contract can be validated, but it's only once it's actually been mined that it's added to the blockchain, and that's when all the other participants on the network will consider it a valid state update.
So for the greeter, when he said hello, it actually wrote hello somewhere in the blockchain, and then we just read that.
Yeah, we were reading it from the blockchain. When we deployed the greeter contract, that deploy method, it's completed only once the greeter contract had been successfully sent to the blockchain and added as a transaction onto a block on the blockchain. Then when we call the greeter.greet, it goes off to the blockchain and then queries it. So you could go to any node at all that's to query that value back, as long as it's in sync with the blockchain.
How many gas units for this greeter, just to get an order of, because you said the gas is like the minimum step, like a CPU cycle.
Yeah.
So how many CPU cycles is the greeter?
I couldn't remember off the top of my head. You can see details of the gas used by the contracts on Etherscan, or any contract, any network explorer. You can see the gas used with the transaction.
How is the gas paid? Through the wallet of whoever executes the program?
The question was how is the gas paid for, and when you submit a transaction, you need to have a wallet associated with that transaction that has Ether to pay for that transaction.
There was a payable value on your JSON file was set to false.
Yeah.
So is it possible to get a smart contract without paying for it?
In Solidity, there's what's called a payable modifier you can apply to methods, which basically says I can send funds to this smart contract. But that's all available in the Solidity documentation if you want to read more about it. Yeah.
Have you ever had issues trying to connect a client to a get node? Like when running locally, I've found, especially through Unix systems like Mac,
Yeah, I personally haven't had any issues connecting to clients, but it just comes down to the transport layer. Yeah. All right. I'm going to leave the questions at that, but if you want to talk any more, sticking around for a bit now. Thank you, everyone.